So this next section is about inverses of functions. Inverse functions are things that you've already used before. We talked about sine of 30 degrees, and if you get your calculator and you go sine of 30, you get an answer of a half. Well, what about if I did sine of what equals 1? How would I figure that out? Well, I'd have to get sine theta by itself and move sine to this side, and I usually write it as sine second function sine to that -1. Hey, wait a second, that looks like this, sine to the -1, theta, f to the -1. Sine to the -1, or now we can say inverse sine, is 90 degrees. That's an inverse function that you're already quite comfortable with. We're going to talk about inverses in other situations that are not trigonometric. We can do inverses in 3 ways. You can simply exchange the x and y coordinates of the function. If you have the equation, then you can switch the x and y's in the equation and isolate for the new y. Or if you just have a graph, you can pretend you have a mirror that goes along the line y equals x, and then imagine what the graph would look like flipped in that mirror. The only thing you have to remember, if you're going to use number 3, the algebraic inverse, for a quadratic function, those are x squareds, you have to make sure it's in vertex form or else you're not going to be able to rearrange it. The inverse of a function is not necessarily a function. Once you take its inverse, it might not be a function anymore. Sometimes they are, sometimes they're not. Our first example. The following ordered pairs belong to the function f of x. 1, 2, 3, 4, 5. Those pairs. Determine f to the -1. Determine the inverse of this function. Graph f of x and its inverse, and then state the domain of both x, f of x, and inverse of f of x. So let's do everything for f of x first. So f of x is -5, 0, -4, 2, -3, 5, -2, 6, 0, 7. So here's our function. If we're going to graph it, -5, 0, -4, 2, -3, 5, 3, 5, -2, 6, -2, 6, and 0, 7, 0, 7. We have our function, we have our points. We want to state the domain and range of both f of x. So let's do the domain. The domain is all the x values, -5, -4, -3, -2, 0. In this case, our function is not continuous, it's a discrete function, so we just put these discrete points. Our range is our y values, 0, 2, 5, 6, and 7. Alright, let's discover our inverse. Our inverse, we denote inverse by putting a -1 right up there. And we said we had 3 ways of doing inverse. We can exchange the x and y coordinates in the function, we can reflect the graph, or we can change the equation. We don't have an equation, so we're not doing number 3. We're going to try 1 and we're going to try 2. 1 says, take these coordinates and switch them. Instead of -5, 0, I have 0 and -5. Instead of -4 and 2, I have 2 and -4. I have 5 and -3. I have 6 and -2. And I have 7 and 0. So if I take a look at this, my domain is all of these new x's, 0, 2, 5, 6, and 7. And my range is all of these y's, -5, -4, -3, -2, and 0. So if you take a look, the domain of the function is the same as the range of the inverse, and the range of the function is the same as the domain of the inverse. It's kind of the definition for what an inverse function is. So this is number 1, switching the x and y coordinates, the first way of finding the inverse of a function. The second way of finding the inverse of a function is to reflect the graph of the function in a line, a specific line. So let's take a minute and plot these points. 0, -5. X is 0, y is -5. 2, -4, 2, -4. 5, -3. 5, -3. 6, 2. 6, -2. And 7, 0. 7, 0. So if we take a look, let's draw a line. Let's draw the line y equals x. That's a line with a slope of 1, and that passes through the origin. Oops, sorry. Not a good line. Bad math teacher. So if you take a look, do you see how these are mirror images of each other? These two are mirror images, if that's my mirror. This is our mirror. We're taking these images and flipping them over to here. So we have one point that's about here on the ruler, and when we flip it, it's still here it is. This is our function, f of x, and here is our inverse that's been reflected, f to the -1 of x, inverse f. So let's try one last example. For the following two functions, determine their inverses, graph both the original function and their inverse, and lastly, determine if the inverse is our functions. So let's take our original function, f of x. We're going to do this guy first. F of x. What kind of function is this? This seems like a linear function. It's a linear function with a y-intercept of -3 and a slope of +2. There we go, there's our f of x. I need to figure out the inverse. So how am I going to do this? Let's do this algebraically this time. I know that f of x equals 2x minus 3. That's my original function. If I want to find the inverse, I have to switch the x and y. I find f of x notation, the function notation, cumbersome. Gets in my way. I'm going to change it back to good old-fashioned y equals 2x minus 3. Okay? Now that I've done this, this is still my original function. To get my inverse, I swap where x and y are. So this is now x equals 2y minus 3. Alright, well, for functions, I want y by itself. I'm going to move the -3 over. That becomes x plus 3 equals 2y. I'm going to divide everything by 2. I get 1/2 x plus 3 over 2 equals y. Alright, is that a function? Yeah, it's a straight line still. Can write it as f of x if we want, but now it's inverse f of x. 3 over 2 plus 1/2 x. So now it tells me that my y-intercept is 1.5, positive 1.5, and my slope is 1 over 2. Rise 1 over 2. Rise 1 over 2. So there's my new f of x. Rise 1 over 2, yeah, about there. So here's my f to the -1 of x. Sorry. So, we've graphed the original function and their inverse. We can check it by taking our good old ruler, making a slope of 1, and taking a look. Does this look like a reflection? Do we see how if we folded this page in half right at that point, the two lines would end up right on top of each other? The purple line is definitely a function. Straight line passes the vertical line test. The green line is definitely a function, passes the vertical line test. These are both functions. Alright, our second function is f of x equals 2x squared plus 16x plus 29. I would like to be able to exchange x and y. So we're going to do y equals 2x squared plus 16x plus 29. I do this because I find function notation awkward when I'm trying to do inverses, when I'm trying to switch. So really what this should be is x equals 2y squared plus 16y plus 29. But I've got y in two separate spots. That's going to give me a big headache. Before I do the inverse, I'm going to put this in vertex form. To get this in vertex form, I have to complete the square. Completing the square. Alright, that was that long process. It had like 7 steps. Alright, first thing I'm going to do is I'm going to take the 2 out of the first 2 terms. So I factored out a 2 from both of those. The next part, I'm going to take this 8, divide it by 2, which gives me 4, and square it. So I get x squared plus 8x, that stays, plus 16 minus 16, and the 29 is still there. I'm now left with x plus 4 squared minus 32. Wait, where did my 32 come from? 2 times negative 16 gives me negative 32. 2x plus 4 squared minus 3 is what I'm left with. Now, I'm ready to do my inverse. I'm ready to switch x and y. I now have x equals 2y minus 4 squared minus 3. Let's get y by itself. Move negative 3 to this side. X plus 3 equals 2 y minus 4 squared. Divide both sides by 2. X plus 3 over 2 equals y minus 4 squared. Next thing I have to get rid of is the squared. I'm going to take the square root of both. But you and I both know that there are 2 answers to a square root. You can take the positive root, or you can take the negative root. Equals y minus 4. My last line, y equals plus or minus the square root of x plus 3 over 2 plus 4, if I bring the 4 over there. So here is my new function. How am I going to graph both of these? Let's first graph our purple quadratic function. This is telling me that my vertex is at negative 4, negative 3, and that it has a stretch factor of 2. So my vertex is at negative 4, negative 3. My next points are 2 up. My next points are 6 up. So 3, 6. So here's my f of x. Oops. This is a weird function. Let's see if we can make it look like our transformation or mapping notation. If we look, this could be square root 1/2 x plus 3 plus 4. This tells us that we have a c of 4. We're starting with the square root function. We have a horizontal compression of 1/2, and we are going to move 3 to the left. So let's do this. Our normal square root function looks like 0, 1, 4, 9, 0, 1, 2, 3. Our new square root function, well, we've got no anything messing with our x squareds, our square roots, excuse me, except for this plus 4. So it's going to be root x plus 4. So we have 4, 5, 6, and 7. On this one, we're going to take our x's and multiply them by 2. And then we're going to subtract 3. -3, -1, eight take away 3, 5, 18 take away 3, 15. So if I plot these points, x equals 4, y equals -3, x equals 4, y equals -3, x equals 5, y equals -1, 6 and 5, oops, done something wrong. Never mind, won't do this.